Hello everyone and welcome back. My name is Mr. Kowald and today I will be going over stoichiometry. I'm going to present the idea of stoichiometry and then I'm going to give some examples related to more of down-to-earth at-home examples of stoichiometry. So what is stoichiometry? If we break the word down, stoichiometry comes from the Greek the stoichiometry, the stoichio part comes from stoichion, which means element. That's the Greek word for element. And metry comes from the Greek for the ending for measurer. So this has to do with measuring elements, right? So taking that and then we apply also to the definition, we read here that the numerical relationships between chemical amounts in a balanced equation are called reaction stoichiometry. So basically we're looking at the numerical relationships between substances in a balanced reaction, a balanced equation. Okay, and so we're looking at how they're related to each other. And so we look at, here it says that the coefficients in a chemical reaction or a chemical equation specify the relative amounts in moles of each of the substances involved in the reaction. And so what that's saying is if we take this reaction here, so this is a combustion reaction, I'm taking this substance here, which is octane, and I'm burning octane in the presence of oxygen, and I'm getting carbon dioxide and water, assuming that this is a complete combustion. And so what this equation, this balanced equation is telling me is the relative amounts of reactants I need in order to get a certain relative amounts of product. So in this, it's telling me if I look at the coefficients are giving me the mole amounts that I need to react together to get these amounts of water and carbon dioxide. So if I have 2 moles of octane, then this is telling me that I need 25 moles of oxygen to react completely with the octane. So if I have less than 25 moles, then I cannot react completely with the 2 moles of octane. So I will only react with less. But the ratio stays the same. So 2 moles of octane require 25 moles of oxygen by that ratio. So if I only have 1 mole of octane, right? So I divide that by 2, I get 1 mole. So then I need to divide this by 2 to get the same ratio. And so I would need to get like 12 and a half. So 12 and a half moles would react completely with 1 mole. So the ratio is always the same. And the same thing with the other ratios as well. So the ratio of 2 moles of my octane, if I completely react 2 moles, then I should produce 16 moles of carbon dioxide. And if I react 2 moles of the octane, then that should also produce 18 moles of water. So the balanced equation is giving you the ratios of the amounts of reactants and products that I need in order for the reaction to be complete, to completely react, okay? And so let me use an analogy that might be helpful here. So the idea here, this is more like a recipe. So in order to make my product or a certain amount of product, I need a minimum number of certain ingredients that I'm going to need to put together. So if we use the analogy of pizza, for example. So what are the ingredients of pizza? Now, I'm going to make this simple. I'm from Chicago. We love our Chicago pizza, our deep pan pizza, and there's a lot that goes into a pizza, right? So, but I'm going to make it simple, and we're going to limit ourselves to crust and sauce and cheese. So we're going to make it a simple pizza. So what do I need to create a pizza? So I'm going to need, let's say we need one crust. So let me write this down. So to make one pizza, we need one crust. And in order to make one pizza, we also need to add tomato sauce. So 5 ounces of tomato sauce. We'll do 5 ounces. Again, this is, I know, I don't know, a Chicago pizza is different, so I get it. So we're going to make it very simple. So 5 ounces of tomato sauce. So I'm going to put TS for tomato sauce. And I need 2 cups of cheese. Right, we're not going to specify the cheese, just cheese. Okay, so this is the ingredients of making one pizza. So if I put this together, I get one pizza. Okay, so this is the ratio, right? So in the same way that the coefficients here are ratios, so here I have ratios, right? So 1 crust, 5 ounces of tomato sauce, 2 cups pizza, or 2 cups of cheese will give me 1 pizza. So then the question becomes, okay, what if I have 10 ounces of tomato sauce? How many pizzas could I make with 10 ounces? Well, if I need 5 ounces to make 1 pizza, then with 10 ounces, I can make 2 pizzas because it's 5 ounces per 1 pizza. So if I have 10 ounces, I could possibly make 2 pizzas with 10 ounces. Or what if I have 3 crusts of pizza? So if I have 3 crusts of pizza, how many pizzas could I make from 3 crusts? Well, if the ratio is 1 crust per 1 pizza, then if I have 3 crusts, then I should be able to make 3 pieces of pizza, assuming that I have enough of these guys here, right? So if I want to make 3 pieces of if I want to make 3 pizzas and I have 3 crusts, well, how many ounces of tomato sauce do I need, right? If I want to make 3 pizzas. Well, here's the ratio, 1 to 5. So if I want to keep that ratio, then to make 3 pizzas, if I have 3 crusts, then I need to triple the amount here. So it'll be 5 times 3, and then I would need 15. So 3 and 15 is the same as 1 to 5. So I need to keep that ratio, right? So if I want to make 3 pizzas, I need 3 crusts, I need 15 ounces of tomato sauce, and how many cups of cheese do I need? Well, I need 2 cups for every pizza. So if I have 1 crust, if the ratio is 1 crust and 2 cups of cheese, then if I have 3 crusts, right? If I have 3 crusts, then to keep the ratio of 1 to 2, then I need 6, right? So because 3 to 6 is the same as 1 to 2, so I need 6 cups of cheese. So in order to create the number of pizzas you want, you need to follow the recipe and keep the same ratios, right? So to make 3 pizzas, I need 3 crusts, I need 15 ounces of tomato sauce, and I need 6 cups of cheese. So in the same way, I can think about with regard to the number of products I want. So if I'm thinking of this in the same way, then I need 2 of these for every 25 of these in order to make 16 of these, right? So if I wanted to make double this amount, so if I wanted to double this amount to 32, then what do I have to do here? I have to double this, because if I need to keep the ratio the same. Right now the ratio is 2 to 16. So if I want to make 32 carbon dioxide molecules, then if I'm doubling this, then that means I need to double the reactant. So I need 4 moles of octane to create 32 moles of carbon dioxide. But if I double the amount of octane, then I need how much oxygen, right? If I don't have enough oxygen, I'm not gonna be able to react all of my octane. So if I have 4 of these, if I double this, then I also have to double the amount of oxygen in order to put these together to create the product, 32 carbon dioxide, right? So if I double the carbon dioxide, if I want to double the carbon dioxide, then I would double the amount of octane, and I would double the amount of oxygen. And then if I double that, then what's going to happen here? Then that's going to be doubled as well. I'm going to double the amount of water produced. And so these coefficients behave as mole ratios. So these ratios must stay the same if I'm going to produce a certain amount of product. Just like if I want to make a certain amount of pizza, then I need to make sure that I'm following the recipe and I'm keeping the ratios of the ingredients. Otherwise, I'm not going to be able to make the number of pizzas I want, right? So I hope this makes sense. So this is a way of understanding balanced equations and chemical reactions. So this is what we call stoichiometry. The relationships of the coefficients to each other stays the same. And so those relationships can help us figure out, well, if I have 16 moles of my octane, how much oxygen do I need? Well, if the ratio is 2 to 25 and I have 16, then I can use the ratio 2 to 25 to figure out the amount of oxygen I need, right? So if 16 is 8 times 2, then I need to multiply 8 times 25 to get the number, right? So eventually what we're going to be able to do is we can use the ratio, the mole ratio of 2 and 25 as a conversion factor. So we've used mole ratios before, right? We use the formula, the mole ratio in our formula, right? So if I use water as an example, so if I use the mole ratio of 1 mole of water gives me 2 moles of hydrogen, I can use that to convert from moles of water to moles of hydrogen, right? So in the same way, I can use the coefficients as a ratio of moles to moles. So 2 moles of my octane will react with 25 moles of oxygen to give me 16 moles of carbon dioxide and 18 moles of water. And that ratio will always hold. So this is what we mean by stoichiometry, using the relationships, the relative amounts of reactants and products to convert from one substance to another in a given problem. That's what stoichiometry is. And it's very, very useful, and you're going to be using it a lot. So I hope this was helpful, and in the next few videos we'll go over some examples of how to use your balanced equation to solve problems. And if you like this video, like the video, write a comment in the comment section. Tell me what you think. What do you want to know more about? Also, make sure you hit the notification bell, subscribe to the channel, and hit the notification bell. And thanks for joining me, and I'll see you next time. Bye.